So, good evening. Today we will be looking into how to do convolution by FFT. Okay. So, why it is important? It is important because we discussed that we perform convolution to find out the output of an LTI system. Okay. So, if you look over here, we are having a system whose impulse response is HT. Okay. If we or HN, say for example, because we are dealing with discrete time Xn, and we get an output of Yn. We also discussed that convolution in the time domain, it is multiplication in the frequency domain, which is quite easy to perform. Okay, so if you look into the convolution thing, so we are having a lot of computation that will be carried out. Now, while we want to analyze any specific system, then we will not be having a short length of the signal. We will be having a large length of the signal. Okay. So in that case, what happens? Suppose your length is say in hundreds, because as I told you, when we discuss about these discrete time signals or the digital signals, having sampling frequency of 1000 is quite minimum. That means you will be handling 1000 data points in 1 second. Okay, so if you want to analyze a 5-minute signal at least, so how many points you will be having? Say 60 into 1000 into 5. Okay, so it's lot of data. So in that case, if you want to do the convolution in the time domain, it will be having, or it will be needing a lot of computational burden. Okay, so in that case, if we use the FFT, and then by performing the FFT, and we just have to do the multiplication in the frequency domain, and then we can find out the inverse FFT. Okay, so let us see how we can do that. Okay, so what happens is that we are having this xn, will be performing the DFT over here. Few moments back, couple of students came, so they were asking what is the difference between DFT and FFT. Please be reminded, I have told you specifically that FFT itself, it is not a transform. Okay, FFT is a method to implement DFT. Okay, so FFT itself, it is not a transform. Okay, so if I ask you find out DFT by implementing DIT FFT or DIF FFT, basically I am asking you to either use the DIT FFT algorithm to find out the DFT, or DIF FFT to find out the DFT. Okay, if I say you find out the DFT, then you have to perform the DFT computation. Okay, because there will be lot of, you have to find out a lot of 12 factor values, then you have to do the matrix multiplications and all these things. So the marks will be higher over there. So if you see in a 5 marks question, if I ask you perform DFT, so you have to do it using that method. But if you see, if I ask you find out the what you call this output of a given system by convolution, by implementing the DFT method, and I specify that you perform it by the DIT FFT method or normal FFT method or DIF FFT method. So if it is given FFT method, you can use either DIT FFT or DIF FFT. Okay. But if I mention DIT FFT, then you have to do it using the DIT FFT butterfly architecture. If I ask you, you do it using the DIF FFT, you have to implement it with the DIF FFT. Okay. So now coming to this linear time invariant system, LTI system. So in the LTI system, as I told you, so our output, it is given by xn convolution of h of n, right? Now if I find out the DFT, I get into x of omega. Similarly, if I perform DFT for h of n, I will be getting capital H of omega. Okay, so this input, it goes into the capital H of omega. From here I will get y of omega, okay, which will be equals to x omega multiplied by H of omega. Now this multiplication, it is point wise multiplication. Okay, point wise multiplication. Getting my point? So it is point wise multiplication. So once you get this y of omega, you have to perform inverse DFT. Okay, you have to perform inverse DFT to get the yn. Okay, so in this way, we are avoiding the complex time domain convolution. Okay, but what you have to do, you have to perform two DFTs and one inverse DFT. Okay. Now coming to the point over here, yesterday we have discussed that when we are doing this FFT computation or the DFT computation for finding out the convolution, so especially we are implementing the circular convolution. Okay. Now when we are performing the circular convolution, we have seen that if we do not choose the length of the signal in an appropriate manner, then what happens? We will be having time domain warping. Okay, so wherein some of the time domain signals, they will be added up and we will be getting a signal which is non-existent. Okay, for that purpose what we did the zero padding. Now over here, if you see, we are having this signal x of n, it was equal to 1 2 3 4. Okay, and we are having h of n 1 to 1. So what should be the length of our output? The length of our output was 4 plus 3 7 minus 1 6. But when we are implementing FFT, we can have FFTs in the order of 2 to the power n. That means we can have FFT of 2-point FFT, we can have FFT of 4-point FFT, we can have FFT of 8-point FFT, then again next would be 16-point FFT and so on, right? Now if you have to implement this, what we have to do now? So you have to see that we cannot go for the 4-point FFT. We have to go for 8-point FFT. So what we have to do? We have to pad sufficient number of zeros so that we are having the total length as 8. Because in an 8-point FFT, you will be needing 8 input points. Okay, so you have to create the signal in such a way such that you are having 8 input points. Okay, so for both x of n and h of n, they will be converted into 8-point signal. Okay, then we have to perform 8-point FFT initially to compute x of k, because k is usually regarded as the what you call frequency domain parameter in physics. Okay, and from there this k is coming. Okay, it is nothing but your x of omega. So we have to compute x of k, we have to compute h of k, Then we have to find out y of k by multiplying. What type of multiplication? Pointwise multiplication of x of k and h of k. So what does this mean? If you see in both the cases, alternatively I have highlighted the numbers. Okay, so the n equals to k equals to 0. I am having 10 over here at in x of k, whereas in h of k I am having 4. So 10 multiplied by 4, I am having at the k value 40. Then in the next thing I am having this imaginary value, and then this imaginary value, they will be multiplied and I will be getting at k equals to 1 that value. Then subsequently this one multiplied by this one, so we will be having the second. Okay. So in this way we will be able to do the thing. Okay, you're getting my point. So now once you get the y of k, then you have to apply the inverse FFT. Okay, so if you see, I have given you a bit reversed order. So this is through the DIT FFT method. So I have given the stage 0, what is the input sequence. Then at the first sequence, after performing the 2-point FFT or DFT, this would be your output. After 4-point DFT, this will be your output, and this would be your final output. Okay. Similarly, for the H of K also, I have uh, reported the values. Then these are the multiplication values, and lastly, you have to perform the inverse FFT to get to the y. Okay, so we get back to the yn signal. Okay, so these zeros, they count nothing. So 0 to 5, if you check, we got 1, 4, 8, 12, 11. Okay, so now you do the numerical. If you have any doubt, you can ask me. You have to first find out the FFT of x of n. Then you have to find out the FFT of h of n. The intermediate values at different stages, these are given. Then from there you have to perform the pointwise multiplication of xk and h of k. And after you have done that, then you have to perform the inverse